So we're going to take a look at some examples for Rolle's theorem and mean value theorem. So for 1 and 2, we're going to use Rolle's theorem to find the c value at which the slope of the graph is equal to 0. And all that means is we're going to be finding the location, the x location of where we have a horizontal tangent. So first thing is, for the theorem itself, we have to have a continuous and differentiable curve. And as you can think about what this graph is, it's quadratic in nature. And so it will be continuous across its whole domain, and certainly across the domain from -4 to +1, from a equals -4 to b equals 1. And the graph itself is differentiable. There's no sharp turns, there's no vertical tangent lines, it's just well behaved. So there should be at least one location, okay, where this graph's slope is 0. And so we're trying to find the point at which that occurs. So let's just go through the mechanics and then we'll look at a visual in just a minute. So to apply Rolle's theorem, yes, okay, all the if statements have been satisfied. It's continuous differentiable as a closed interval. Okay, then what we're going to do is we're going to just verify that the two y values at a and b are actually the same. Because if they're the same y value, when we subtract them, we're going to get a slope across this entire interval of 0. So let's go ahead and verify that our y values are the same so we can use Rolle's theorem. So the first thing I'm going to do is I'm going to evaluate the function at b. And when I plug in 1 everywhere I see x, if I did the quick calculations, I'd get 0. Let's look at the y value at -4. If I plugged in -4 and did the calculations here, I'm also going to get 0. So we can see that the difference between these two y values is 0, and so from one endpoint to the other, the graph is just going straight across. Okay. Alright, so now to use Rolle's theorem, all we have to do is find the derivative and set it equal to 0. We're looking for locations where the slope is 0. So I'm going to come down here and take the function, find the derivative. Easy enough, 2x plus 3. If you wanted to, you could go ahead and replace every x with c. So now we're just using the same variables that the theorem has. Alright, so where is this derivative equal to 0? Where is f prime of c equal to 0? So I'm going to replace f prime of c with 0, and then I'm going to solve. I'm going to subtract 3 and divide by 2. So when I do that, I'm going to get -3/2. And I'm going to pause here for a minute, and I'm going to make certain that -3/2 is a value that falls between a and b. And it does. It checks. And so we can say that this is the location, at least the x value, at which the slope of the tangent line would be 0. So let's get a visual of what that is over here. Okay, so we're looking from -4, perhaps -4 is over here, and 1 is right here. And remember, we went ahead and found the y values over here, so f of 1 is 0, so that's the point here. And f of -4 is also 0. So we have these two x-intercepts. They just happen to be on the x-axis, and that's fine and everything. Okay, so if I wanted to draw the curve through here, we know it's a parabola that opens up, so it probably does something like this. So what we found over here was the x value, -3/2, so maybe this is -1, -2, -3, so -3/2 would fall about right here, going down to the curve. Okay, this would be the location on the graph of this parabola at which the slope, this is -3/2, okay, the slope of the graph right here at -3/2 is equal to 0. So we found the c value at which we have a horizontal tangent line. That's all Rolle's theorem is. We've been doing problems of that nature, and so now we're just putting a name to it. Okay, so let's look at another example. All right, using Rolle's theorem here, let's locate the c value between 1 and 2. So this is A, and this is B. Let's find a value that fits between 1 and 2 such that the slope of the tangent line is 0. So if we're told we can use Rolle's theorem, just find the derivative, set it equal to 0. First, let's verify though. What's the functional value at 1? When I plug 1 in everywhere I see x, it looks like I'm going to get 64. Let's evaluate the function at 2. Okay, when you plug 2 in everywhere and do the calculations, as a matter of fact, you also do get 64. So these are 2 points on the graph, and the average rate of change from x equals 1 to x equals 2, if I did delta y over delta x, would be 64 minus 64 over 1 minus 2. That would give me 0. So I can use Rolle's theorem because this is continuous and differentiable on this interval, and these two y values are the same. So let's proceed. Find the derivative, set it equal to 0. If you want to replace every x with c, you can. It's not necessary. You could just set this equation equal to 0 and you're good to go. Okay. So let's find the horizontal tangent, at least the x value. I know these are both divisible by 16, so that would give me 3 over 2, 3 halves. Just double checking, does 1.5 fall between 1 and 2? If it does, it's a good solution. If it doesn't, if we introduce a c value down here that doesn't fall between these two x values, then it's an extraneous solution. We'd still want to show the work that we did to get to it, but we would just like mark it out and put a big X on it. It's extra solution. Okay, so we just found the c value at where the horizontal tangent occurs. Okay. This looks like, if we were to get a graphical representation of it, this looks like it's a downward opening parabola. And we're considering the interval from 1 to 2. Okay, and you don't have to do this, I'm just getting a graphical illustration of what's going on. It appears that if I called this 64 here, I would plot the point 164. Likewise 264. I know the graph opens downward, so, and it told us, putting all this together, that 1.5 is our c value at which we have a 0 slope. Well, I'd have to draw the graph up this way, or the point up here at this point. Okay, and draw it continuing down like that, because I know this graph has a maximum, and it must occur right here at that c value. So right here, f prime of 3 halves is equal to 0. Now if we wanted to know the y value at which this horizontal tangent is occurring, if I wanted to know what the y value was, then what I would do is I would evaluate the original equation at 1.5. But we're not asked and we're not directed to find the point, the x and y coordinates, so we're good to go right here. So Rolle's theorem, find the derivative, set it equal to 0. All right, let's take a look at the use of the mean value theorem in the next couple of examples to find c, an x value, such that the slope of the graph at that c is equal to the slope of the secant line through the endpoints. So now notice that this is not f prime of c equals 0. It's probably going to be some other value here, and we're going to have to find that average rate of change. All right, so here's our example. Consider the function x squared plus 1 on a to b. This is a, and this is b. Let's find c such that the derivative is equal to the slope given by delta y over delta x. So that's the first thing we're going to have to do. We're going to have to find the functional value at 2, f of b. So plugging 2 in here, I'm going to get 2 squared 4, 5. Let's plug in negative 1 here to the function. Negative 1 squared, 1 plus 1 is 2. Alright, so what is the slope between these 2 points on this graph? Well, we might as well go ahead and calculate that. So let's do f of 2 minus f of negative 1 all over 2 minus negative 1. So this is just delta y over delta x, f of b minus f of a over b minus a. So it's going to look something like this when we do the calculations. F of 2 is 5 minus 2 over, and here in the bottom we can go ahead and clean that up, we get 3. So it looks like 3 over 3. It looks like we're looking for where the slope is 1. Now let's go ahead and start to get a visual over here of what's going on. It's easy enough to look at x squared plus 1. So something like this. That's the function. Now remember, we're considering the interval from negative 1, perhaps over here, to positive 2, somewhere over here. We calculated the y value, so f of 2 is 5, so we'll call this point right here 2, 5. And f of negative 1 is the point negative 1, 2. Alright, so negative 1, 2. Alright, well, what does this 1 represent? Well, it's actually the slope of the line through these two endpoints that we're considering on this closed interval. So if you will, just kind of consider that secant line. That's the secant line through the two endpoints as determined by these a and b values. Alright, well, where on the graph between negative 1 and positive 2, where on the graph, and just this section right here is all I care about, where, at what location is the slope of the graph the same as this value? Alright, well, I know it wouldn't be down here at the vertex because the slope there is 0, so it's going to have to be somewhere on part of the graph where it's increasing. I'm just going to estimate that maybe about right here. Remember, this is just an estimate. Our numerical value will take care of it here. Our numerical work will take care of it in a minute. But I'm just trying to get a visual. Let's just look at maybe that point and consider the slope of the tangent line. I'm looking for a tangent line that's parallel to, say, this secant line through the endpoints. Okay, parallel lines have the same slope. Alright, so we've got a visual now. We know what the slope is between the two endpoints by calculating delta y over delta x. Now all we have to do is find the derivative and set it equal to the slope of 1. So finding the derivative, easy enough, 2x. Now f prime, I'm going to go ahead and, I'm going to go ahead and change it to c, everything to c here. So I have 2c. So where is the slope of the graph equal to not 0, but equal to f of b minus f of a over b minus a? Well, f prime of c has to equal to 1. So where is 1 equal to 2c? Let's solve. C is 1/2. Just double checking, is 1/2 a value that fits in our interval? It sure does. 1/2 is about right here. So it appears that I was off a little bit. If we were to go over to where c is 1/2, which is about right here, and go up to the curve, it appears that the tangent line through that point, okay, would be the tangent line that's parallel to the secant line. It has the same slope as the slope through the endpoints. So just kind of risky when you do graphs, especially with this kind of software. Okay, so this is our answer to the problem. That's our c value at which the two slopes are equal. The secant line and the tangent line have the same slope. Alright, for the next example, same situation. We want to find on the interval from a to b, the interval from 0 to 1, where the slope of this graph right here is equal to the slope of the secant line. So the first thing we're going to do is evaluate the function at the endpoints. So 1 to any power is 1. Plug in 0 to the function. 0 to any power, or 0 to 2/3, of course, any power is going to be 0. Alright, so let's find f of b minus f of a over b minus a. So what's f of 1 minus f of 0 over 1 minus 0? Well, these are all working out really nicely here. F of 1 is 1, f of 0 is 0. It's kind of a coincidence. 1 minus 0, so that slope is 1. It's kind of unusual that I've chosen two examples here that have the same slope. Didn't mean for that to happen, but just know that you're not always going to get 1. Alright, let's go ahead and look at a visual of this too. I'm going to begin to look at the graph on the interval from 0 to 1. I know f of 0 here is 0 and f of 1 is 1. So I have 0, 0, 0, 1. And actually this part of the graph here, it has a sharp turn at the origin and it comes off of it. You could produce on your calculator, it goes something like that. Okay, so changing colors here, what's a graphical representation of the value of 1? Well, it's actually going to be the slope of the line through the endpoints like this. So that's the secant line. So where on this curve, okay, would the slope of the curve be the same as the slope of this line? I'm not going to dare try and find that c value. I didn't do so well in the last one, so we'll just kind of let it play out. Alright, so back to what we need to do. First thing we did is we calculated the slope. Next thing, let's find the derivative using the power rule, replacing every x with c. Again, you don't have to. And along the way, I think I'm going to clean this up too. So it'll be 2 over 3 times the cube root of c. Alright, so now next what we're going to do is we're going to set this derivative equal to the slope of 1, because we're using mean values theorem, not Rolle's theorem. Otherwise it'd be set equal to 0. So f prime of c is going to be replaced with 1. Want the slope to equal 1, and then we're just going to perform the calculations. So you might want to do cross products. So 3 times the cube root of c equals 2. Let's see, I guess I'll divide both sides by 3. So I'm going to have the cube root of c equals 2/3. And I'm going to cube both sides now. So let me come up here. If I cube both sides, I'm going to have c equals 2/3 cubed. And just double checking that value to make sure it fits between my a and b values. 2 cubed is 8 and 3 cubed is 27. Ooh, I'm glad I didn't try and approximate that. But I do know that 8/27 does fall between 0 and 1. So that is going to be my answer. If I think about this right here, I think it's a little bit less than 1/3 of the way over. So I would think that graphically it might be about right here somewhere. Okay, and so the slope of that line is going to be the same as the slope of the secant line. So I just located the c value, which is 8/27, at which the slope of the graph is equal to the slope of the slope through the endpoints. So hopefully you found that these 4 examples, 2 for Rolle's and 2 for mean value theorem, kind of helped you to see how the theorems might work in particular problems.